Hi, this is Mr. Warden. I'm going to talk through a little bit about the cheat sheet on types of linear equations with a particular focus on how they apply to word problems. So on this sheet, I've got a cheat sheet. There's the first page is for these two forms, slope-intercept form, y equals mx plus b, and the standard form, that's the 5D stuff, ax plus by equals c. Okay, and then on the next sheet, on the next page, I have the intercept form, x over the x-intercept plus y over the y-intercept equals 1, and y minus y1, this is the point slope form, y minus a known y value equals m, the slope, times x minus a known x value from the same point we got the y value from. So essentially, this is a change in x for any x value that's on the line and its corresponding y value. So x minus a known x and y minus a known y. This is just rearranging the slope formula. And this is explained down in here. So what I want to do is I want to talk about what this is all about. So the slope-intercept form has a rate. So slope is a rate, okay? And it's the change in output divided by the change in input. It's like miles per hour or pay per hour and a variety of other things. It could be rates. It could be percent interest on the amount of money you've invested. It could be the percent of cases of COVID there are in the population. It could be there's a lot of ways that the slope could be used as a rate. Now the y-intercept here, this is where x is 0. And since x is often time, that means that the y-intercept is often a starting place. Or should I say, at a starting time, where you are when you start. So, for example, if you start off a period of time having $5,000 in the bank, and every day you spend $40, we could make a slope-intercept form equation that goes like this. Y equals the $40 you spent, so that's negative 40 times x, and then plus the amount of money you started with. And then we could plot a graph to see what happens with your money over time if this is all that you do. So I'll open up a Desmos so you can see that play out. Okay, and we can use this to model this. So we can say y equals negative 40x plus 5,000. Now, this graph is not visible to us right now. We have to zoom out to get to where 5,000 is. Okay, and somewhere up here, there's 5,000. So that's our starting point. And then we can actually figure out if we're spending $40 a day, how much time it takes to run out of money. After 125 days, you will have run out of money. This is sort of an end place. And this brings to mind a different equation form, which is the intercept form. So if we go back here, I'm going to hop around a little bit. I'm going to go down to the next page, to the intercept form. So this is best when you know the x-intercept and the y-intercept. Okay, now I'm going to delete that in a second because y'all should work this out yourself, but that's what goes in here. It's best when you know the x-intercept and the y-intercept. Okay, those go away. Now, I notice in this Desmos graph, I now know the x and y-intercepts. I know an y-intercept is 5,000 and an x-intercept is 125. So I could rewrite this using the intercept form. X over 125, because that's how many days it take me to run out of money, plus y over 5,000, and that will always equal 1. And there I have the same equation. It's just this time I'm using the intercept form. Now, this So the setup on Desmos is a little hard to look at. So I'm going to go ahead and change a little bit here. So I'm going to change the x-axis. Currently it's from negative 10,000 something to positive 10,000 something. So I'm going to make it negative 50 and then make that positive 200. And that's a little easier to look at. I've just changed the scale. You might notice I'm going by 50s here, but here I'm going by 2000s. So this is a little easier to see and we can work things out. Okay, so the intercept form is really cool because it allows us to come up with a graph when we have a starting time and an ending place. So this is like the place, so this is how many days it took us to, maybe it's an ending time and a starting place. That would be a better way to put it. Starting place and an ending time. Now we're starting, that's time is the start, but our place is $5,000. And we have an ending time after 125 days, we have nothing in the bank. So you could have an intercept form for those sorts of situations. I'm going to go back to the linear cheat sheet and let's take a look at, and so, another way to put this is starting place, y-intercept, and an end place. That could be an x-intercept. Now, sometimes you might have a starting place or let me change that. Ending time, I should say. Starting time, maybe that's in the past. That could be an x-intercept that's negative and an ending place. Okay, so that could be a y-intercept. Okay, so maybe you started digging a hole 43 days ago, and today you are now 60 feet underground with this hole. So we could actually treat that as a starting time 42 days ago and an ending place 63 feet below ground. So we can create an equation that models that. We have a starting place, negative 42 days ago, and an ending time, starting time and an ending place. Let me say that again. We have a starting time way back in the day, 42 days ago, and now we have an ending place where y over negative 63 feet underground, and that equals 1. Now I'm going to have to change this a little bit and zoom out a little bit now. So this will model that 42 days ago, I started digging my hole, and today I have reached 63 feet underground in my efforts to dig my hole to the other side of the earth. How many of y'all have tried that when you were a smaller person? Okay, so that is another manifestation of the intercept form. All right, the other two, the point slope form, the point slope form is a good one for when you have something that could be represented as a point, or maybe you have two things that can be represented as a point. If you have one thing that can be represented as a point and you know a rate, then you could use the point slope form, treat that point as the point and the rate as the slope. Or you might have 2 points and you have to figure out the rate. Okay, so this point slope form is a good one when you might have a time and an output related to the time and a rate, or 2 times and outputs related to those times. You have to figure out the rate based on those 2 situations. Okay, I will lay out a scenario like that really quickly here. So let's say 5 days into your journey, you had a stash of 400 energy bars. Okay, and then notice I'm not giving you a y or x intercept this is I'm giving you a point that is 5 days, and you have 400 energy bars. Okay. You consume them steadily at a rate of, we'll say, 3 bars a day. That means -3. The number is going down. So that means a slope of -3. So we'll come back to that. Okay. So once we have that information, now we have a slope and we have a point. So we can come up with a point slope form. We could say y minus 400 equals, and since I'm eating them, I'm not producing them, it's -3 bars per day is my rate, and then x minus 5. And I now have an equation that I could go here and take a look. I've got my 400 energy bars, and I think these energy bars will probably last me for a reasonable amount of time because, after 77 days, I should now have still have around 180 some odd energy bars. And it looks like we can use the graph to figure out how long it'll take me to run out of energy bars. I have energy bars for a little more than 138 days. That's pretty awesome. Okay, now I'm going to change the story. Okay, turn that off. I'm going to change the story. Now, instead of knowing the rate, I'm going to have 2 checkpoints. So 5 days in, we know that you consume them at a steady, we're going to say okay, 5 days into your journey, you had 400 energy bars. 40 days into your journey, you had, we were going to, let's say 75 energy bars. Okay, you have. Okay, so let's just take a look at what that means. So we've got this point 400, but we've also got another point, 40, 75. 40, comma, 75. So we've got these 2 points that tell us something about how fast we're using the energy bars. So there's a point at 40, 75, and somewhere up here is a point at 400. So what we need to do is we need to find the slope between those 2 points, and then we can make a point slope form. So 400 minus 75 is the change in y, 400 minus 75. So I've got a change of y. If I'm actually, let me do it the other way around because I'm going forward in time. So I'll say, and so we are going to have a negative 75 minus 400. So we get negative 325. And then our x value, since we did 75 minus 400, we got to do 40 minus 5. So I'm going to say 40 minus 5. Okay. And so it looks like we have roughly we're eating a little more than 9 energy bars a day. So let's simplify. That's 35. And that one here was negative 325. And we can factor 5 out of both of those. And let's see, what's 325 divided by 5 is 65. So we'll simplify that to negative 65 over 7. Okay, so it comes out to, looks like we've got 9 2/7 energy bars we're eating every day. So I'm going to use the fraction instead of this and create an equation. So I can pick this point or the other point. I will pick this point for this purpose. So y minus 75 equals negative 65 over 7, which is that negative 9 2/7 times x minus the x value there, which is 40. And now I have an equation that will model how many energy bars I would have had at any particular time, assuming a steady rate of consumption, and it can project how many days it'll be before I run out of energy bars. So on day 48, I run out of energy bars. Okay, I could have used the other point, which was 400. So that's a 400, and that's a 5, and that works too. One more equation type, and that is the standard form. The standard form works like this. It's something times x plus something times y equals c. And this is really useful when instead of one rate, we have two rates. So I'll give you a scenario where that makes sense. So we turn those off and unlabel the points. So let's say you went for a trip, and you went for a trip for some period of time at 4 miles an hour. Okay, I will actually make that. Okay, went on a trip. You went. I'm going to change that number. A trip, and for part of that time, you went 40 miles per hour, and for another part of the time, you went 50 miles per hour. Over the course of the trip, you traveled 2,000 miles. Okay, so we can actually create an equation based on this. We don't know how long we went 40 miles per hour, and we don't know how long we went 50 miles per hour. So let's call the amount of time we went 40 miles an hour x hours. So we can say 40 miles per hour times x hours is some distance. And we also know we went 50 miles per hour for some other amount of time. So we can say 50 miles per hour times y hours is the other part of the distance. And those two distances add up to 2,000 miles. And so we can create an equation that models the possible combinations of hours. So if y is 0, so if we actually went 0 hours at 50 miles per hour, then we would have had to have gone 40 hours. I'm sorry. If we'd gone 0 hours at 50 miles per hour, that's actually over here because y is 0. We would have had to go 50 miles or 50 hours at 40 miles per hour. And I'm actually going to change this number. I'm going to make that 1,000 because that'll actually illustrate something a little better. Zoom in more. Zoom in a little more. Okay, so in this case, the overall trip was 1,000 miles. And so we can click on here, and we can see that if we went 0 hours at 50 miles per hour, then we would have had to go 25 hours at 40 miles per hour. And if we went 0 hours at 40 miles per hour, we would have had to go 20 hours at 50 miles an hour. And you can go through here and you can find the different combinations of hours that would have worked. So 7 hours at 40 miles per hour and 14.4 hours at 50 miles per hour. And you notice I keep mixing it up in my wording that I keep saying miles or hours. It's useful to write this stuff down. I'm not writing it down, and that's tripping me up. So y is the number of hours I went 50 miles per hour. X is the number of hours I went 40 miles per hour. Miles per hour times time is a distance. We have two distances involved, a distance that we traveled at 40 miles per hour and a distance we traveled at 50 miles per hour. And those two distances, which we don't know because we don't know what X and Y are, those two distances do add up to 1,000. So that is a standard form tool. I'm going to stop the video because it is getting long, and I hope that this was helpful for you with word problems.